All right, 2-4, we're talking about logarithms. This is a whole new type of math. It's going to feel a little bit weird, but it's actually very, very easy. A couple rules you got to remember. Some applications of logarithms. There's two areas where you've probably heard of logarithms without even knowing that you were hearing about it. Whenever you hear the news or whatever talk about earthquakes, earthquakes are measured with magnitude, and this is actually uses logarithms. And then also, if you've ever heard about the measurement of sound in decibels, this is also something that uses logarithms. Just some application there for you to understand what it's for. All right, what is a logarithm? Well, log, y equals log base b of x. That's how you say this. This is log base b of x. If and only if b to the power of y equals x. So essentially, all you really do is you kind of just flip these two things and drop the log. So base b to the power of y equals x. This is a way of rewriting an exponent as a log so that we can get the exponent all by itself. That's the whole point here. And again, how do you say it? You say log base b of x. All right, so let's rewrite it. Let's practice rewriting it. So remember the number down here, this is our base, and this number is the exponent. So to rewrite this, I'm just going to write 3 to the 5th. It's 243. See, I've written it in exponent form. All right, over here, I have log base 5. So I'm going to do 5 to the power of 3 equals 125. That's it. All right, so I want you to practice these two on your own. Go ahead and check your work and unpause the video when you're ready to check your progress. So this would be 9 to the 0 equals 1. And this would be 1/2 to the negative 4 equals 16. And that's true because remember, negative exponent means you just flip the base. So this is the same thing as saying 2 to the positive 4 equals 16. And that's true. Okay, so that's rewriting from log to exponent. Let's go the other way around. Let's take these exponents and write them in log form. So I would say log base 3 of 9 equals 2. Over here, log base 2 of 32 equals 5. That's all this is. It's just a way of writing exponents, rewriting exponential equations so that the exponent is all by itself. That's all this is. So go ahead and try 7 and 8 on your own, and then unpause the video when you're ready to check your work. Okay, so this would be log base 5. The exponent is 0, so it goes over here, and that's 1. So log base 5 of 1 equals 0. Over here, you got to think about how you can write this as an exponent. And remember that anything to, like you can rewrite this as an exponent of 1/3. So whatever the number in the crack is, that's what I like to say, that's the number that goes on the bottom. So once you rewrite this as an exponent, you can say, okay, well, the base is 64. It's of 4, so log base 64 of 4 equals my exponent of 1/3. All right, now let's try to evaluate these. And sometimes it helps if we can rewrite it. So like on this one, I know, like if I was to say this equals x, and I was to rewrite this in exponential form, I'd be like, okay, so that means 2 to the x equals 8. And this might help you figure out what the answer is, because then you can kind of think, okay, 2 to what power equals 8? Well, 2 squared, we could just kind of go through this, like 2, 1 equals 2, 2 squared equals 4, and 2 cubed equals 8. So 3 must be my answer. So the answer here is just 3. So rewriting it can help you evaluate it sometimes. How about on this one? Let's say I make this x. This is like saying 7 to what power equals 1/7. Well, remember, in order to just flip the base, you need to make this a negative. So this would just be -1 because 7 to the -1 is the same thing as 1/7. All right, so rewrite them to evaluate these two logs on your own. Go ahead and try these two on your own. Okay, both of these are a little bit tricky. So I rewrote it like this. It's 1/3 to the x equals 81. At first you might be like, well, this doesn't make any sense. How do I get this to be an 81? Well, let's think about negative exponents because negatives flip it, right? So if x was -1, this would be 3 to the -1. It would just be 3. Or it'd be, it'd be 1/3 to -1, so this would just be 3. So how do I get 3 to 81? Well, I know 3 to the 4th equals 81. Therefore, 1/3 to the -4th equals 81. So the answer here is -4. It's a little confusing. If you need more help with that, ask me about it in class. Here, I'm going to write this as 25 to the x equals 5. So basically, I'm saying what exponent makes 25 into 5. Well, the square root of 25 is 5, and that's like saying a 1/2 as an exponent. So x must be 1/2. All right, I know it's a little bit getting used to. We'll have more practice with it in class. All right, let's talk about a couple things here. There's two types of logs that show up very commonly. One is what we call literally a common log, and that's whenever the base is 10. So we don't even write the base in that situation. We literally just write log x. So if you ever see a log without a base, it's because the base is 10 and we're not going to write it. We don't have to write the 10 there. We skip that. The other thing you might see is a log with a base of e, like we learned about in the last video. If you see that, we write that as lnx, and that stands for, I know it's backwards, it's the natural log, or the log natural of x. So that's called the natural log, or the natural logarithm. These two will show up commonly, but you need to know this is just base 10, and this is just base e. All right, let's practice with the calculator. Literally, you're just plugging this into your calculator. Everybody has a little bit different calculator, so you need to find the button that says log on yours. And so since this is log 13, we're really saying log base 10. Your calculator knows that if you just type the log button. So find the log button on your calculator, then press 13, and you should get, I'm going to do it on mine real quick, log 13, you should get 1.113943352. What does that mean? That means 10 to this exponent would equal 13. I want you to do the same thing for the natural log of 6. You should find that button somewhere. So just literally ln of 6, and you should get 1.7917594, running out of space, 469, okay? Just try that on your calculator. If you're not getting that, then you need to come see me so I can show you how to use your calculator. Couple things that you need to know about logs, some simplification rules that you need to know. These both just equal x, but I want to explain why. So let's talk about why. Let's start with this first one of log base b of b to the x, and let's just call it y. So this is what's inside my log. Remember, to rewrite this, I would write this as b with the exponent y equals the thing inside the log b to the x. And then you could see the bases are the same, therefore the exponents have to be the same. So I said it's equal to y, but we just established y and x are the same, and so that's how I know it's equal to x. So essentially what happens here is that, like, this log base b and this base b, they cancel each other out, and you're left with just what's in the exponent. And the same thing is going to happen here. Like, these guys are going to cancel each other out. Why? Let's play with it. Let's see why. So I have b to the exponent of log base b of x. So this whole thing is the exponent. If I was set this equal to y, I can now write this. It's in exponent form, even though it's a log in the exponent. This is technically exponent form. So I can write this in log form. So I'm going to do log base b of y then would equal the exponent, which is log b of x. And once again, everything else is the same, therefore these are the same, so this must equal x. That's why, but just know these things cancel out. So as I look over here, and I look at this problem, this is really, this is just a log 6, so this is log base 10. So these cancel each other out, and you're just left with 6. Now this, at first, doesn't cancel each other out, but we can rewrite it. Oh, does that make, hopefully I just want to make sure you got that. This is 10 to the log base 10, so these cancel each other out, and we just left with what the exponent is. Here, it's not going to cancel out so nicely, but here's the deal. Can we rewrite 9 as 3 to an exponent? Yes, it's 3 squared. So if I rewrite this, I got log base 3, 3, and really if I have this to the power of x, when you have an exponent to an exponent, they multiply. So this becomes 3 to the 2x. So what's going to happen? Well, this log base 3 and this base 3 cancel out, and you get just what's in the exponent. That's it. So that one we had to rewrite first, but then it did cancel out nicely. I want you to try these two on your own. Give it a shot. You may not get it, but remember, this is simply this, e to the log base e of 3 to the x. And this is really log base e of e to the x over 2. Maybe that'll help you understand what's going on here. That's all ln e, or all ln is just a log with base e. So give those two a try and then check back when you're ready to check your work. So once you see it written like this, you should see that this e and this log e cancel each other out. You're left with whatever's in the exponent. It's 3x. Same thing here. This log base e, this e as a base, cancel each other's out. And we're left with the exponent of x over 2. Let's go to the next page. Okay, now we're going to talk about graphing a log. Well, a log is really just an inverse of the exponential equation. So if I was to try to graph, I'll do it in blue, this function here, all I really have to do is reflect it across the line y equals x, because this is its inverse. So everything will just reflect. So I can do that. If I reflected across this line, I'd have these 2 points. Rather than having an asymptote along the x-axis, I'm going to have an asymptote along the y. So it's going to look something like this. Boom. All there is to it. The same thing is true if it's decaying. Okay. See, this is where b is greater than 1, and this is where b is less than 1, but greater than 0, so some fraction. We get this decay. Well, the logarithmic function, again, is just going to be a reflection of this. It's going to look a little weird, though. I'll do this one in another color. I'll do it in black. So if I reflect this point, it's going to go right there. But if I reflect this point, it's going to go like right there, wherever b is. So your reflection is going to look something like this. Okay, the graph got a little bit off. And now you can see how this literally just does a crisscross across the line y equals x. So it's literally a reflection of the original function or the base function, because these are inverse. So that's one little trick to graphing these, is to graph the exponential and then just flip it. But let's talk about how we can graph a typical log function, what we want to do. Before I graph this one, what I want to do is I want to come over here and just talk about a basic one. What if I had the equation y equals log base b of x? What you want to do is you want to pick x's that are really easy to plug into. To make it really easy, we know that if I had b to some exponent, the base b and the log base b would cancel out to just be the exponent. So let's choose to do that. Let's do like b to the -1, b to the 0, b to the 1, b squared. What would you get? Well, you would just get out -1, 0, 1, and 2. So we're going to use that to our advantage. So we're not going to plug in a typical 0, 1, 2. We're going to take our base to that exponent so that we can get out something really easy to graph. So we go back to this problem now. With that in mind, let's make a little chart. I'm going to use 4 to the -1, 4 to the 0, 4 to the 1, 4 squared. That's 1/4, 1, 4, and 16. See how I'm picking x values that are easy to plug in here? What am I going to get? I'm just going to get out, because what I'm going to have, like for example, with 4 to the -1, I'm going to have log base 4 of 4 to the -1. Everything's going to cancel out. I'm going to be left with the exponent. So I get -1, 0, 1, and 2. Now I have some points that I can graph, right? So let's take a look at this. When x is 1/4, I'm at -1. When x is 1, I'm at 0. When x is 4, I'm at 1. And when x is at 16, I'm at 2. But that's way off the graph here. And we can tell that we're going to have an asymptote here on the x, no, not the x-axis, sorry, the y-axis. But I want to explain to you why. Why can it never cross this line? So let's play with this idea. And let's just kind of think. What does this really mean, right? So I have y equals log base 4 of x. But if I was to take this equation and write it in exponential form, I'd have 4 to the y equals x. And let's think. Remember, these are when my x value is negative. So let's just kind of ask ourselves, all right, so like 4 to what power equals a negative, let's just say like -1. Is there anything that you can put in for the exponent here that would make 4 to that exponent a negative number? Any negative number. Maybe it's not just -1, maybe it's -4. And the answer is no, you can't use an exponent to make this negative. Like, think about what you could do. You could do like 4 to a really big number, 100. And that's definitely going to be, you know, not a negative number. That's going to be some number that's greater than 0. Sorry. So that's not going to be a negative number. That won't work. Let's try 4 to like a negative number. If I did 4 to a -1, that just makes 1/4. If I did 4 to like -10, all that really does is do 1/4 to the 10th, which is a very small number, but it's not negative. So that's why there is no way to get a negative number, and that's why you'll never have anything on this graph, and that's why we have an asymptote right here. So that's kind of how that works. Just hopefully you can kind of see why we get an asymptote here. All right, so what does that mean my domain is? That means that it's all x values greater than 0. What's my range? The range is all real numbers. And the reason why it's all real numbers is we can see, remember, range is y. We can see it definitely goes down forever this way, and this will go up and up and up. Now, it's not going to go up very fast, but it is going to continue to go up. So there's my domain and range. Now, that's just the basic version. Now, what if we get something a little bit trickier? What if we get something like this? Here's what you want to do. You want to graph, or not really graph, but you want to make a chart of the basic function here. So ignore the 2 and the -1, and let's make a little chart for y equals log base 3 of x first. Well, we're going to do the same thing we did before. I'm going to do 3 to the -1, 3 to the 0, 3 to the 1, 3 squared, which is really 1/3, 1, 3, and 9. And when I plug those in, remember, I'll just get out these exponents. So I'd get out -1, 0, 1, and 2. Okay. But that's not the function I want. I want this function. So let's think about what we did here. We have an h and we have a k. And remember, there's a minus in front of that h, so it's always opposite of how it looks here. So we know now that the h is -2 and the k is -1. Well, all we have to do then is just add the h to our x values, the k to our y's, and we'll have our new points. So for example, 1/3 minus 2, that is -1 and 2/3. -1 and -1 makes -2. Do this for all these points. 1 minus 2 is -1. 0 minus 1 is -1. Hopefully you're seeing a theme here. 3 minus 2 is 1. 1 minus -1 is 0. 9 minus 2 is 7. 2 minus 1 is 1. And these are the points we want after we did this shifting, okay? So let's plug this all in to my graph. It looks a little ugly. That's better. -1 and 2/3, comma -2 is about here. -1, 1 is about here. 1, 0 is here. And 7, 1 is off the graph, but we could kind of estimate it's going to be somewhere over here. And we get something like this. We're still going to have an asymptote here. And it turns out that the asymptote will always just be x equals whatever your h is. So remember, my h is -2 because it's the opposite of how it looks. And so that's how I knew that I have an asymptote there at -2. What's the domain? Well, now that I have it sketched, I can see the domain is x values greater than -2. Let's do it in blue. And the range is still all real numbers. Which, by the way, you could write that as all the values from -infinity to +infinity. That's fine. All right. I'm sure you might have some questions for me in class. We could play with this more. It's definitely different, but it's not that bad. You'll see. It's pretty easy stuff. All right, see you guys on the next video.